Om. Hello everyone, I am Shri Jyoti. Welcome to my channel. Today's video is of class 11 mathematics chapter 14 probability. See, about probability we have already studied in our small classes, right? So probability is nothing but it's a chance. It is the measure of likelihood of an event to occur. Okay, in our early classes we studied about random experiment and sample space in probability. See, what is the random experiment? See, in an experiment, if there is more than one possible outcomes and it is impossible to predict the outcome in advance. So, such experiment is called random experiment. So, what is the sample space? Sample space is nothing but it is the set of all outcomes. Is called the sample space. Okay. So, here in this chapter, these all things we studied in our early classes. So, in this chapter, we will study here events. Okay, about events. See, events is nothing but it is the set of any set, okay, any subset. We studied what is a subset in sets, okay, any subset of a sample space, okay, any subset of a sample space is called an event. Let us consider an example. Consider an experiment of tossing a coin, okay, tossing a coin twice. So what is the associated sample space? Sample space is denoted by S. See, associated sample space is HT, TH, HH, TT. Okay, these all things we already studied. So here, when we tossing a coin twice, so the associated sample space is HT, TH, HH, TT. Okay. Now here we will consider. See, what is the occurrence of exactly one head. Okay, occurrence of exactly one head. See, I will write exactly one head means see only HT, TH. So, HT, TH. So, it is called an event. Okay. So, this is called event. It is the example for event. So, here that is it is the subset of a sample space S. Right. So, any subset of a sample space is called an event. So, here there are many types of events. So, first we will study impossible event and sure event. See, impossible event means, see the set, empty set, okay, empty set and sample space is called impossible event. And sure event, in sure event means, see the sample space, the whole sample space is called sure event. See, here also let us take one example. Let us consider an experiment of tossing a die. Okay, rolling a die, not tossing coin, okay, rolling a die. So consider an experiment of rolling a die. So here what is the associated sample space? See, associated sample space is nothing but 1, 2, 3, 4, 5, 6, right? So here, see, I will take an example, that is event, okay. Let E be the event, let E be the event. See, in this event, the number appears on the die is a multiple of 7. Okay. My event is the number appears on the die is a multiple of 7. Okay. It's my event. See, can you write the subset of associated with this? Can you write the subset associated with this? Cannot, right? See, because we know that, see, it is the sample space. Okay, because there is no element. Okay, there is no element is multiple of 7 in this sample space. Right? Because we know that here 1, 2, 3, 4, 5, 6 up to 6. See you? So here the set E is nothing but, the event E is nothing but null set. Okay, so such event is called impossible event. Okay, so let us take a sure event, example for sure event. So here also let us consider an experiment, same experiment of rolling a die. Okay, so here the sample space, associated sample space is 1, 2, 3, 4, 5, 6, and the event, let us take an event F. Okay, F be the event, the number turns up is even or odd. Okay, I have taken an event, number turns up is even or odd. See, clearly the event F is equal to 1, 2, 3, 4, 5, 6. Right? We will get the event F is nothing but even or odd. So we will all the elements will come, right? So this F is nothing but whole sample space. So such event is called sure event. See, the next event is simple event. Now we have already explained these impossible events and sure events. See, impossible event is nothing but that is the event has no element, that is empty set, okay? And sure events is nothing but it is the whole sample space. So what about the simple event? Simple event is nothing but an event has only one sample point of a sample space, that is only one element from the sample space. See, for example, let us consider an experiment of tossing a coin twice, okay? So the associated sample space is HH, HH, TT, TH, HT, okay? So here let us consider an event appearance of exactly two tails, okay? Appearance of exactly two tails. That is, see here only one element we can write in the event, right? So if the event has only one element or one sample point of a sample space is called a simple event. That means that event has only one element, okay? One sample point of a sample space. So what is the compound event? Compound event is nothing but an event has more than one sample point of a sample space is called a compound event. See here, for example, occurrence of at least one tail, okay? At least that, let us take an event occurrence of at least one tail. At least one tail means, see, we can write all these three elements, right? At least one tail. So TT, TH, HT. See here there are three elements, three sample point of a sample space. So such events are called compound event. Next we will study algebra of events. See, in our first chapter sets, we discussed about the combining of two or more sets. That is union, intersection, difference and complements of a set. So likewise we can combine two or more events also. So here let us see. See, first one is complementary event. See, complementary event means the complementary set, that is complementary event means it is denoted as a complement. See, for example, sample space S is equal to HH, TH, HT, HT, TT. Okay, so here suppose A is equal to HH and TH, okay, then the A complement is nothing but, see, what are the elements except these elements in sample space? So that is HT and TT, okay, so that is the complementary event, okay. So next is the event A or B. A or B means A union B, okay. So remember, or means union, okay. The event A or B, that means A union B. And the event A and B, that is nothing but A intersection B. It is A union B. So the event A and B means A intersection B. Next, the event A but not B. Event A but not B means A minus B, okay. So now let us go through some example based on this. Look at this example. Consider the experiment of rolling a die. Let A be the event getting a prime number and B be the event getting an odd number. Write the sets representing the events. First one, A or B, A and B, A but not B and not A. Okay. See, first of all, let us write the sample set. Okay. That is a sample space, that is associated sample spaces. See, what is the experiment? Experiment of rolling a die, right? So the associated sample space is 1, 2, 3, 4, 5, 6, right? Okay. Now, what are the events given? See, given events are, first event, that is, let's say A is equal to, event A is getting a prime number. See, what are the prime numbers in sample space S? A is equal to prime numbers in sample space is 1 is not, okay, 2, 3, 5. So 2, 3 and 5 are the prime numbers in S. Okay, and event B. See, what is the event B? B be the event getting an odd number. So what are the odd numbers in sample space? 1, 3, 5. Okay. Okay, now here, see, events, we have to write all these events. A or B. A or B means A union B. So what is A union B? A union B is nothing but A union B, that is all the elements of A and B. Okay. So 1, 2, 3, 5. That's all. Okay. Now next is A and B. So what is A and B? A intersection B, right? So it is first one. Second one, A and B means A intersection B, that is equal to intersection of A and B. 1, 3, 5, 2, 3, 5. So 3, 5 are intersection elements. That is 3, 5. Common elements are 3 and 5. So A intersection B is 3, 5. Next is A but not B. A but not B. That is what are the elements in A but not in B. Okay. See, 2 is in A but not in B. 3 is in A, 3 is in B, 5 is in A, 5 is in B. So only the element 2 is in A but not in B. Therefore, A but not B means A minus B. Okay. So what is the element? Only 2. Okay. Next is not A. See, not A is nothing but complement of A. Okay. That is complementary. So not A is complementary event. Not A means, remember, not A is nothing but complement. A complement. That is not A is equal to A complement. That is, see, what are the elements in S but not in A. Okay, A complement is nothing but the elements in S but not in A. So what are the elements? 2, 3, 5 are here. So 1, 4, 6. 1, 4, 6. Now we are going to study mutually exclusive events and exhaustive events. First one, mutually exclusive events. See, in these events, when we take two events, when we take the intersection of two events, it should be an empty set. Okay. That means, say for example, let us consider an experiment of rolling a die. So sample space is 1, 2, 3, 4, 5, 6. Okay. So here let us consider two events A. An even number occurs. An even number appears. Okay. Event B, an odd number appears. Okay. See here, see what is the set A? Event A is, elements of event A is nothing but an even number, right? So 2, 4, 6. 2, 4, 6. So what about B? B is nothing but 1, 3, 5 because the event B is defined as an odd number appears. Okay. So here what is the A intersection B? A intersection B is an empty set, right? So there is no element, there is no common element in A and B. Okay, so here we have got A intersection B is equal to an empty set, that is null set. Okay, so such sets are called, see here A and B are called mutually exclusive events. Now what about exhaustive events? See here let us consider the same example that is the same experiment of rolling die. Sample space is 1, 2, 3, 4, 5, 6. So here let us consider the events. First event A, number less than 4. less than 4 appears. Okay. Next, second event, number greater than, okay, greater than 3 appears. Next, event C, number greater than 4 appears. 4 appears. Okay. So here we have defined 3 events. One is number less than 4 appears. Okay. Now let us write what is A. See, what are the elements in event A? Number appears less than 4. Okay. Number less than 4 appears means, see here 1, 2, 3. Right. 1, 2, 3. Okay. Now what about B? Event B, elements containing elements, that is number greater than 3 means 4, 5, 6. 4, 5, 6. Next event, third event C, consists number greater than 4 appears. Greater than 4 means 5, 6. Okay. Now, so what is the union of these 3 sets? A union B union C is equal to A union B union C. 1, 2, 3, 4, 5, 6. 5, 6. So union is nothing but 1, 2, 3, 4, 5, 6. So it is nothing but the sample space, whole sample space. So here we have got the union of 3 events. These all events A union B union C is nothing but the whole sample space. So such events are called exhaustive events. That is, in generally we can say if E1, E2, E3, etc., En are the events of the sample space, then E1 union, E2 union, E3 union, etc., union En is equal to yes. In these events are called exhaustive events. Okay. Suppose these are exhaustive events, then E union, E1 union, E2 union, E3 union, etc., union En is equal to sample space yes. Now let us go through some questions. First question, a die is rolled, let E be the event, die shows 4 and F be the event, die shows even number. Are E and F mutually exclusive? See, what are mutually exclusive events? The intersection of 2 events is an empty set, then we say two events are mutually exclusive events, right? So here the experiment is a die is rolled, okay, rolling a die. So the associated sample space is nothing but 1, 2, 3, 4, 5, 6. Okay, now let us write what are the events. Given events, E is equal to E be the event, die shows 4. That is, the only one element of E is 4. Right? Now what are the elements of F? F be the event, die shows even number. Okay? Die shows even number. So what are the even numbers in S? 2, 4, 6. 2, 4, 6. Okay, see here. Now let us find E intersection F. Intersection of 2 events E and F. That is, E intersection F is nothing but the common element is 4, right? So 4. So it is not an empty set, right? Therefore, E and F are not mutually exclusive events. So our answer is E and F are not mutually exclusive events. Because here we have got E intersection F is equal to 4, not equal to null set. See the next question. An experiment involves rolling a pair of dice and recording the numbers that come up. Describe the following events. A, the sum is greater than 8. B, 2 occurs on either die. And C, the sum is at least 7 and multiple of 3. So here, question is, which pairs of these events are mutually exclusive? Okay, see, when a pair of die is rolling, then the sample space is, see here, two pair numbers are in pairs, okay, that is 1 1, either 1 1, okay, these are the possibilities, 1 1, 1 2, 1 3, 1 4, 1 5, 1 1 6, so like that 6 1, 6 2, 6 3, 6 4, 6 5, 6 6, okay, so total there are 36 elements in this sample space. Now let us write the events. See, events, A is nothing but, A is the sum is greater than 8. See, the sum of pairs is greater than 8 means 9, from 9, starting from 9 to 12, right? Because last number, that is greatest number is 6, 6. So, till 12, okay? Sum till 12. So, here first number is greater than 8. So, it will not possible. So, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, okay? Greater than 8. So, 2, 6 is not including, okay? From 9, right? Okay, so here 3, 1, 3, 5, 3, 6, 3, 6, 4, 5, okay, 4, 5, sum is 9, okay, 3, 6, sum is 9, 4, 5, sum is 9, 4, 4 is not including because 4 plus 4, 8. Here the sum should be greater than 8. So 4, 6 is the element of A. 5, 1, 5, 2, 5, 3, 5, 4, 5, 4, then 5, 5, 5, 6, okay, 5, 6, 5 plus 6 is 11, so it's greater than 8. Then 6, 1, 6, 2, 6, 3, 6, 3, 6, 4, 6, 5, 6, 6. Okay, so these are the elements of event A. Next, let us write B. B is nothing but 2 occurs on either die. That means, see, 2 occurs on either die means the number 2 appears either first die or in second die. Okay. So here the numbers 1 2, 1 2, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, okay, after that 3 2, 3 2, 4 2, 5 2, 6 2. That's all. So here these are the elements of event B. Next, event C, the sum is at least 7 and a multiple of 3. The sum is at least 7 means the sum is greater than or equal to 7 and multiple of 3. Okay. Now here let us consider multiple of 3 first, because multiple of 3 means only small number of numbers are there, right? That is multiple of 3 means 6, 6 and 12, right? 6, 9, 12. So 6 is not possible. So here at least 7. Their sum is at least 7. Therefore 6 is not possible. So 9 and 12, right? So what are the numbers will come? Addition of two numbers will be 9. Multiple of 3 or sum is 9 and it's greater than 8, right? So what are the numbers? Let us write. C is, first one is 6 is not possible. So we have to find 9. Addition should be 9. So 4, 5 is okay. 3, 6. Okay, let us start from here. 3, 6. 3, 6. Then 4, 5. Okay. Then 5, 4. 5, 4. Okay. We have to check. The sum should be 9. The pairs, their sum should be 9 and 12. Okay. 9 and 12. So 6, 3. 3, 6, 4, 5, 5, 4, 6, 3. Then 6, 6. Okay. These are the elements of C. Okay. Now let us check whether these pairs are mutually exclusive or not? Which pairs of these events are mutually exclusive? Okay, now let us see A intersection B. See A intersection B, 3, 6, 1. Are there any common elements? 3, 6, 4, 5, 4, 6, 5, 4, 5, 5, 5, 6, 6, 3, 6, 4. So no common elements in A and B. Therefore, we can say A and B are mutually exclusive events. That means there is no common element in A and B. Therefore, its intersection is 0, right? Not 0, an empty set. Okay, null set. Therefore, they are mutually exclusive events. Now, let us see these two. B intersection C. What about B intersection C? Here 3, 6, 4, 5, 5, 4, 6, 3, 6, 6. Okay. So here also B and C there is no common element B in B and C. Therefore B and C are mutually exclusive. Since B intersection C is null set, therefore B and C are mutually exclusive events. Then what about A intersection C? A intersection C has common elements, right? C 3, 6, 3, 6. So here we cannot say A intersection A and C are not mutually exclusive events. So here A and B are mutually exclusive events and B and C are mutually exclusive events. Next question. 3 coins are tossed. Describe 2 events which are mutually exclusive, 3 events which are mutually exclusive and exhaustive, 2 events which are not mutually exclusive. So here the conditions are given. So we have to find the events according to this. So here first of all let us write the sample space. When 3 coins are tossed, the sample space is S is equal to, first let us write H, H, H. Okay, 3 head. Then H, H, T, H, T, H, T, H, H. Then T, T, H, T, H, T, H, T, 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 T. Okay, so these are the possibilities when 3 coins are tossed. So sample space, these are the elements of a sample space. So here, now let us write one by one. Say first one, we have to write 2 events which are mutually exclusive. Okay, so we will write the event A getting, because mutually exclusive means when we take its intersection, it should be null set. Okay, there should not be a common element in A and B. Okay, 2 events getting exactly 2 heads. Okay, exactly 2 heads means, see, HHT, HTH, THH. The elements are, okay, I will write here HHT, HTH, THH. Exactly 2 heads, right? So over. So now let us write, see, according to this statement, 2 events which are mutually exclusive. So we should get A intersection B, or intersection of 2 events should be an empty set. That means there should not be even a common element, right? So here now let us take the event B getting exactly 2 tails, right? So the elements will be TTH, HTT, THT, right? So here when we take the intersection, so there will be no common element. Okay, so let us take B as getting exactly 2 tails, so that we will get, there will be no common element in A and B. 2 tails means, see here, TTH, THT, HTT, right? So here, see, its intersection is an empty set because there is no common element in this A and B. Okay. Now let us go through second one. Second statement is three events which are mutually exclusive and exhaustive. So it should be, we have to write three events mutually exclusive. Okay, it should be mutually exclusive. That means intersection of them and their union should be exhaustive. Means their union should be the sample space. Okay. So here, now let us write A. Okay. Let us write getting at least two heads. Okay, at least two heads. So what are the elements? At least two heads. So H, then T. At least two means greater than or equal to 2, right? HTH, THH. Okay, at least two heads. So next let us take B, getting at least two tails. Okay, getting at least two tails. See, we have to write the events. See, so that their intersection should be an empty set. Okay, at least two tails. See, so that its intersection will be an empty set. There will be no common element in both sets, right? That is at least two tails. At least two tails means from here. Okay, TTH, THT, HTT, TTT. Okay, then so see what we will take. See, all the elements are done here, right? THT. So okay, so here let us take exactly two tails. Okay, exactly two tails, so that this element will not include in this set, right? Okay, so next we will take, because see, its intersection should be an empty set. Okay, so there will be no common element. Therefore here if we take at least two tails, see, all the elements are done. So here we have to take one more event, so that we will get the intersection will be one common element, right? So here let us take C as getting no head. Okay, getting no head. So that, see, we can write TTT. Okay, only TTT. Getting no head. So we can write TTT. So here these all elements we cannot write, because our event is getting no head. So only TTT is the element of this event. Now see, here take the intersection. See, when you take the intersection of these all sets, we will get an empty set, because there is no common element in these three sets. And what about union? A union, B union, C, you will get, it is nothing but sample space, right? So all these elements will be coming after taking the union. HHT, CHH, HHT, HTH, THH, TTH, THT, HTT, last one TTT. So these are the mutual exclusive and exhaustive events. Okay. Now here, last one, two events which are not mutually exclusive. Not mutually exclusive means, see, we can write the two events when we take the intersection. Okay, its intersection is not an empty set. Okay, so how to write? I will write here two events which are not mutually exclusive. So one element including, okay, or one or two, more than one, okay, which are not mutually exclusive. So here we can write getting getting at least one head. At least one head. So what are the elements? At least one head means, see here we can write TTH, THT, HTT. Okay, these are the elements of A. Because at least one head, okay, greater than or equal to 1. So next here we can write at least one tail, getting at least one tail, so that we will get a common element, at least one tail. See here, at least one tail means here we can write this also, HHT, HTH, THH. Okay. So here when we take this intersection, see we will get common elements. That is, see all the elements are common elements, right? Okay. So these are the examples for according to these statements.